Have you ever stopped to think about how you actually measure the properties of a measuring tool itself? It's kind of a puzzle, right? Well, today we're going to solve it. We're diving into a classic physics technique, the half deflection method, to uncover the secrets hidden inside a galvanometer. Here's the game plan. We'll kick things off with the central mystery, then look at the tools we need. After that, we'll get into the two main parts of the experiment, finding the galvanometer's resistance, G, and then its sensitivity, what's called its figure of merit, or K. And to wrap it all up, we'll see how all the numbers come together. So, yeah, this is a classic physics problem. You can't just take an ohmmeter and hook it up to a galvanometer to find its resistance. Nope. The current from the ohmmeter would probably destroy the delicate little coil inside. So we have to get clever. We need an indirect method to see what's really going on in there. Okay, so what is a galvanometer? It's the heart of so many electrical meters. It's an incredibly sensitive device built to pick up on the tiniest electric currents. But here's the catch. That sensitivity means its own internal resistance can actually mess with the very circuits we're trying to measure. And that's exactly why we need to know its properties down to the last detail. So the technique we're going to use is called the half deflection method. And honestly, it's such an elegant solution. It uses a parallel circuit in a really smart way to figure out the galvanometer's internal resistance. We create a very specific condition where the current splits in a way that we know perfectly. Now, the absolute key to this entire experiment is something called the shunt resistor. I want you to think of it as a detour, or maybe like a bypass lane for electricity. By putting this low-value resistor in parallel with the galvanometer, we're giving the current an easier path to take. And controlling how that current splits between the two paths, that's the whole secret to this method. And here it is. This is the circuit we'll use to find the resistance. You can see we've got our power source, E, and this high resistance box, R, which is super important for controlling the current and protecting the galvanometer. And right there, connected in parallel across the galvanometer, that's our star player, the shunt resistor, S. We can switch it in and out of the circuit using that little key. Okay, circuit's ready. Let's get into the detective work. Mission number 1 is to figure out the precise internal resistance of our galvanometer, which we're going to call G. The logic here is it's beautifully simple. So, step 1. With the shunt disconnected, we play around with that high resistance R until the galvanometer's needle swings to a big, easy-to-read spot. We'll call that deflection theta. Step 2. Now we connect the shunt resistor S. What happens? Well, the current now has two paths, so it splits, and the needle drops. Step 3. This is the crucial part. We carefully adjust the shunt's resistance until that needle points to exactly half of where it started, theta divided by 2. Now, if you were doing this in a lab, you wouldn't just do it once. You'd fill out a table just like this one, repeating the whole process with different starting resistances. And for each try, you find that very specific shunt value, S, that gets you to that perfect half deflection. And if you look closely at the data here, you can see the value for S is staying really, really consistent. That's a great sign. And all that careful work in the lab, it all boils down to this one elegant formula. When the deflection is cut in half, it means the current has split pretty much equally between the galvanometer and the shunt. And this formula right here, G equals RS over R minus S, is the math that lets us calculate G from the numbers we just measured. So, just to quickly recap what's what. G is our mystery value, the resistance we're trying to find. R is that big series resistance that we control. And S is that magic number, the specific shunt resistance that gave us our half deflection. It's as simple as that. Excellent. So we've cracked the first secret of our galvanometer. We know its internal resistance, G. But now it's time for part 2, finding out just how sensitive this thing really is. To do that, we need to find its figure of merit. The figure of merit, which we call K, is a straight-up measure of sensitivity. It tells us exactly how much current we need to make that needle move by just one single division. So think about it. A smaller K value means the device is way more sensitive because it takes less current to get a reaction. So to find this sensitivity, we actually get to simplify our circuit. We don't need the shunt anymore, so we take it out. Now it's just a simple series circuit, our power source E, the resistance box R, and our galvanometer G, whose resistance, you'll remember, we now know. The process for this part is alarm direct. All we have to do is adjust the resistance R until we get a nice, big deflection that's easy to read. Once we've got that, we just write down 3 things: the battery's voltage E, the resistance R we're using, and the deflection theta that it caused.
And those three measurements plus the value of G we already found let us use our second key formula. The figure of merit, K, is equal to the total voltage E divided by the total resistance of the circuit, that's R plus G, all multiplied by the deflection, theta. So K is our goal here. It's calculated from the voltage E, the resistance R we set, and the deflection theta we saw. But look closely. This whole calculation hinges on knowing G from the first part of our experiment. It's a perfect example of how in physics, everything you discover becomes the foundation for the next step. All right, we have the theory, we have the procedure. Now let's see what the final results of an experiment like this look like when we actually start crunching the numbers.
You know, this table really shows what good science is all about. You don't just measure something once. By taking a bunch of readings with different resistances, you can calculate K for each trial. Then you can average all those values together to get a final result that is way more accurate and reliable.
So based on our sources, after you do a few trials and take the average, a pretty typical result for the galvanometer's resistance, G, would be something right around 70.8 ohms. And for the figure of merit, K, you're going to get a really tiny number. In this case, it's 2.19 times 10 to the minus 5 amps per division. And that tiny number is exactly what we want to see. It confirms that this galvanometer is incredibly sensitive. It takes almost no current at all to get it to move. Of course, getting clean results like this means you have to be careful. A few precautions are absolutely key. First, make sure all your connections are nice and tight. Use a stable power source so the voltage doesn't change on you. And maybe most importantly, always start with a really high resistance for R. Think of it as a safety valve that limits the first jolt of current and protects that delicate coil inside the galvanometer. So why did we go through all this, you might be wondering? Well, this is way more than just a textbook exercise. By knowing its internal resistance G and its sensitivity K with such precision, we have everything we need to actually transform this device. We can now confidently engineer it into a practical tool, like a custom-built ammeter or voltmeter for a specific job. We figured out its internal character, and now we can give it a purpose.